So, 4.8. It is, give me a plus if you're seeing my screen all right there. Would you? It deals with what's called L'Hopital's rule, right? And L'Hopital's rule is a way of evaluating certain unusual limits, okay? We use it to evaluate limits that are what we call indeterminate. Okay. So the best example I can give you of what we mean by indeterminate is it's a number that we can't figure out the values. So real simple, silly example is, what's a million plus a million, right? No, not a million plus a million. That's easy. That's too big. How about an infinity plus an infinity, right? Infinity plus infinity. So a really large number that goes to infinity plus a really large number that goes to infinity. Now that may seem like it's still infinity, and that's pretty simple, but what about like infinity minus infinity? That's, when you think about that, you're not able to, it could be anything from infinity to negative infinity, depending on which of the first infinities dominated the other one, which one got bigger faster. So that's an example of an indeterminate form. How about this one? What is 0 times infinity? Now, of course, when we're talking about these forms, we never truly mean 0, and we never truly mean infinity. What we mean is something that is going to 0. It's getting smaller and smaller and smaller, and something that is going to infinity is getting bigger and bigger and bigger. So something tiny that's getting tinier times something big that's getting bigger. What is that going to equal? Well, again, that's going to equal anything from 0 to infinity. Okay? So that's what we mean by indeterminate. There are these situations that we just don't know what it equals. And they show up in limits, right? Because we're talking about something going to 0, something going to infinity. And so let's just look at an example here. So we want to find the limit as x goes to infinity of e to the x over x. All right? I think what we'll do today is we'll try to do some of these examples, and then we might even try to squeeze in some stuff that for the next section. So we'll try to cover 2 sections briefly to give you a flavor of both. All right? All right, so here we go. Notice this limit. Where x is going to infinity, it's getting bigger and bigger. And so what that means is e to the x is also going to infinity, and x is going to infinity. So we would say that this one is going to infinity, and this one is going to infinity. So this is an example of an indeterminate form of the form infinity over infinity. What is that going to equal, right? Because basically the top and the bottom are both getting bigger, but the question is which one is getting bigger faster. That will determine what this limit is equal to. So L'Hopital's rule can only be used in 2 situations. Well, we've got a variety of situations, but this is one of them. If you ever end up with a limit where the top goes to infinity and the bottom goes to infinity, you can use L'Hopital's rule. All right? So let's do it. L'Hopital's rule says this: if you need to find this limit, and it's of the indeterminate form infinity over infinity, L'Hopital says what you can do is you can instead find the limit of this. Just take the derivative of the top. We're not using the quotient rule. Just take the derivative of the top. So the derivative of e to the x, let's put that down here. That is d dx of e to the x, right? So you just take the derivative of the top, and you just take the derivative of the bottom. And of course the derivative of x is just 1, right? And now you evaluate that limit. And if you can evaluate it, then you've got your answer. Then these 2 things are going to be equal. So I look at that limit and I say, oh, the top is still going to infinity, right? But the bottom, 1. So infinity over 1 is simply infinity. And there's our answer, right? A really big number over 1 is going to be just infinity. Okay, so that's an example of L'Hopital's. Let's try it again here. The limit as x goes to infinity of 3x squared minus 2x over 2x squared plus x minus 1. I know we've actually done these kinds of limits before, but L'Hopital's actually makes them much simpler. All right, so again we notice as x goes to infinity, this term, this entire top is going to infinity, right? Because x squared is dominating. And the bottom is going to infinity as well, right? So we are of the form infinity over infinity. We are of that indeterminate form. So we can apply L'Hopital's, which says simply this. Find the limit as x goes to infinity. Now just take the derivative of the top, which is easy, 6x minus 2, and the derivative of the bottom, which is 4x plus 1, and now try to find that limit. Well, we have the same thing going on. This one still goes to infinity, this one still goes to infinity. So if I want to evaluate that indeterminate form, which is infinity over infinity, I can apply L'Hopital's again. So L'Hopital's just says take the derivative of the top, which is 6, the derivative of the bottom, and now find that limit. Well, since everything is a constant there, it's just 6 over 4, or 3 halves. There it is. Okay. L'Hopital's is very handy for that kind of thing. Okay. Now, this one we could have done without L'Hopital's. We have some tricks for dealing with these kinds of limits, but they don't. L'Hopital's is another tool for us. All right. Give me plus ones if that makes sense. All right. Some things rolling here. All right. All right. So let me show you another one. The limit as x goes to 1 of square root of x minus the cube root of x over x minus 1. Okay? So, this one, if we tried to evaluate it, we would notice that the top is going to go to 0, right? Because you end up with the square root of 1 minus the cube root of 1. That's 1 minus 1. That's going to 0. And the bottom is going to 0. So this gives us a second indeterminate form that qualifies for L'Hopital's. So we've already talked about the infinity over infinity case, but you can also use L'Hopital's in the 0 over 0 case, and that's where we're at. So we use it the exact same way. We just say, okay, I just take the derivative of the top, which is going to be 1/2. It'll be 1 over 2 square root of x, right? That's the derivative of square root of x. Minus the derivative of cube root of x is 1/3 x to the negative 2/3. So we'll just put x to the 2/3 there on the bottom. And then the derivative of the bottom is just 1. Okay. Now, let's try to evaluate it by plugging in a 1. When you plug in a 1, you get a 1/2 minus 1/3, right? Because the square root of 1 is 1, and x, or 1 to the 2/3 is 1. So you get a 1/2 minus 1/3 on top, and a 1 on the bottom. You have evaluated it, right? We just, do a little fractional addition. This is what? 3/6 minus 2/6 over 1. So that turns into just a 1/6, and there's our limit. very nice, very handy. It works in the 0 over 0 indeterminate case. Okay, so L'Hopital's rule, same game, but it applies to the 0 over 0. So you're going to see in this section those kinds of limits that fit into the the infinity over infinity, or the 0 over 0 case. All right. Now, L'Hopital's works for those, but we have other indeterminates that you're going to run into. So, for instance, let me show you this one. The limit as x goes to where did I see it? Limit as x goes to 0. Sorry, I had one right there, and now I'm just perplexed that I've lost it. Oh, there it is. Limit as x goes to infinity of x minus e to the x. Okay. So, now, as we look at this one and we imagine x getting bigger and bigger, we notice that this becomes x goes to infinity and e to the x goes to infinity. So this is the indeterminate form that we have there. This is going to basically infinity minus infinity. Okay, that's one of those weird things. Now, L'Hopital's rule only applies to infinity over infinity or 0 over 0. Those are the two that we've looked at so far, right? But this one is that indeterminate case of infinity minus infinity, okay? So here's what you do. We actually have several other indeterminate cases. Let me list them here, right? So we can either do, we'll run into, in addition to the ones we've already talked about, we might have also 0 times infinity, right? So if we end up with a limit that ends up in that form, infinity minus infinity. How about this one? 1 raised to the infinity power, or in other words, something that is going to 1 raised to something that is going to infinity, or infinity raised to the 0 power, or 0 raised to the 0 power. All of these are kind of secondary indeterminate forms that we can use L'Hopital's rule to use, or to evaluate, if we can change them to 0 over 0 or infinity over infinity. Okay? So that's the hope, is that we can maybe change it to 0 over 0 or infinity over infinity. Okay? And then use L'Hopital's rule from there. Okay? So we might look at something like this. Let's take this example. Well, let's think about this for a second. Is there a way we can, I guess we ought to throw this in here as well. Remember, you can always use the graph of these, and I don't know if I can. Let's see what I'm using. I think you're still seeing my screen. That's the way I've got this set up. But I'm going to Desmos and graphing this guy real quick. Because remember, whenever you're finding these limits, you can always look at the graph and see if you can learn from the graph. Too many keywords. None of them are the right keyword. Let's try that. All right. Give me what I want here. This particular keyword. Oh, I just want to use this. Let's do this one. looking for the exponential button. Why am I missing it? They don't put it on this keyboard. If I just do that, just back it. Okay, so there's our graph. Oh, you're not seeing it yet, of course, because I've got to do this. Sorry, we're working with a brand new system here, so just get this rolling. Okay. All right. So there's our graph. Fine. Right? So as the limit as x is going to infinity, so in other words, x is going to infinity, it sure looks like that graph is going to negative infinity. Right? It looks like that graph is going to negative infinity. Let me just double check. I'm just double checking here. So, let's see. I want to do this one. If we do it this way, so let's see. The limit, because really what we've got to do here is we've got to get it into one of these forms in order to apply L'Hopital's rule. All right. So there are some odd ways of doing this sometimes. Like for this particular problem we have here, right? Let's just take our expression. No, we're doing this. The limit as x goes to infinity of x minus e to the x. Now, this is the same as this. The limit as x goes to 0 of 1 over x minus e to the, or minus 1 over e to the x. Well, let's see. Is that going to work for us? You know what? I'm going to have to come back to this one. I'll have to work this one in the examples because I'm just not seeing it right at the outset of how to do this. I don't want to waste any more time since we don't have much time as it is. So let me see if I can find that example or work that up as an example video for you. The idea is that if you get any of these other indeterminate forms, you've got to put it in. You've got to be able to write it as a fraction. Okay, and so we do odd things to write these things as fractions sometimes. Of course, they have to be equivalent. We can't just change them. So, like for instance, you might write it like this: x is the same as 1 over 1 over x. Right? That's the same thing. Okay. E to the x is the same as 1 over 1 over e to the x. Right? Those are the same thing. So that's still equal. Right? Limit as x goes to infinity. We're just playing around here a little bit before we totally call it. Now, what happens here is, oh, that's minus. Okay, so if we just look at this one, you end up with some minus. So you end up with some kind of odd things happening here. But that's the same thing, and that's the kind of thing we want to do, is sometimes rewrite these things so that they're still equivalent, but they can be written as fractions. Okay. And sometimes I'll come back to that. I'll work on that one and send you out an example of that. Okay. Let's do this. I want to introduce you to the next idea you're going to see in 4.10. Okay, in the time we've got remaining. Are you guys still with me? Give me a plus in chat if you're still there. It's so strange. I don't know if you're there. I'm sure you're giving me 100% attention. Let's do this. All right, so let's do this. This is a key section. 410 is critical. All right, so that's why I really want to talk about it. This provides the gateway for the rest of the stuff we're going to do in this semester. So we are talking about what are called antiderivatives. Antiderivatives. All right. So an antiderivative. We've been taking derivatives, right? So we do stuff like this. So if I take the derivative of 3x cubed minus 7x squared plus 2x minus 9. We know how to do that easy enough. That's 9x minus 14, or 9x squared minus 14x plus 2, and we're done, right? That is taking the derivative. Well, an antiderivative is working in the other direction. It's where we give you this, which you can assume is a derivative, and we want you to find this. Okay, so we're just working in reverse. All right? We're working in reverse. Okay, so let's just see how this works. Find the antiderivative of f of x, or just, what does it say? Y equals, no, we'll do f of x, we'll just keep it simple, equals 3x squared, right? Okay, super simple. So you have to imagine what function was there, and very often we'll use this notation. Since that is f, then we'll use capital F as its antiderivative. Okay, so that's kind of the notation. You've got a function, its antiderivative will be the capital version of that. So what function has this as its derivative? Well, we know how our derivatives work, and we might just say, oh, well, of course it's x cubed, and we could check it, right? Take the derivative of this guy, and yeah, you get 3x squared. Okay, so there's an antiderivative. Now, we have one little thing that we've got to hit right here. Certainly, the derivative of this is this. So, right? But also, if there was a plus 4, right? The derivative of this would be this, right? Because the derivative of x cubed plus 4 is just 3x squared, right? Or maybe if that was not a plus 4, but maybe that was a minus or a plus 7, right? Again, the derivative of this is this, right? So here's what we have. The antiderivative of 3x squared is not just x cubed. What we do is it could be x cubed plus any constant. And so the way we write that is we just write x cubed plus c, with the understanding that c is a constant, okay? And that's the antiderivative, okay? So let's try it again. Let's say g of x equals x to the 4th. No, let's do 1 over x, right? What is its antiderivative? Well, what function has a derivative that is 1 over x? And so this one we have to remember, oh, it's ln of x, right? ln of x, and then plus Okay, we'll talk more about that a little bit more. It's actually ln of absolute value of x, because we want to make sure we stick with absolute values. But that's it. Remember that plus c. All right, h of x equals the cosine. Well, what is its antiderivative? Well, what function has the derivative of cosine? The answer is sine. Right? Plus c. Yeah, so can it be a minus? Yeah, the way we would do that is we would just add a negative 3, right? So yes, it becomes a minus 3, but by just adding any number, positive or negative, that covers the plus or minus situations. Does that make sense? Just a plus works for that, if that makes sense. Yeah, so C covers all of the bases, so we don't have to worry about doing a plus or a minus there. We just say C can be positive or negative. Now, let's introduce a little bit of notation. If I want you to find the antiderivative, I'm going to do this. I'm going to use this little integral sign, the indefinite integral. So suppose I want you to find the indefinite integral of 5x to the 4th. Okay? So I put a little dx there. So this is the whole package. So you're going to have that symbol and that symbol. And in between those symbols, you're going to have the thing you're trying to find the antiderivative of. Okay? And so that's what this is, right? In other words, when you see that notation with this little integral sign and this dx, we'll explain what the dx means. But right now, that is me telling you find the antiderivative of 5x to the 4th. So, of course, we kind of think about it a little bit, and we say, oh, well, what function has a derivative of 5x to the 4th? Oh, it's just x to the 5th, right? Just take the derivative, you get 5x to the 4th plus c, right? So there it is. Okay, so obviously we're going to get more complicated in finding the antiderivatives of things. So let's deal with that right now, or at least start dealing with it. So I want to find the antiderivative of, here's an easy one actually. Antiderivative of e to the x, just e to the x plus c, right? No big deal. Okay, let's get a little more complicated. What's the antiderivative of, say, x to the 3rd dx, right? Now, I will say this, we use antiderivative, but another word we use here is integral, the integral of x to the 3rd. All means the same thing. Find a function that has the derivative x cubed. All right, so if we think about this, we can start putting it together a little bit. We know it must be an x to the 4th, right? Because if you're going to end up with an x cubed as your derivative, then you probably needed to start with an x to the 4th. But it can't just be x to the 4th because the derivative of x to the 4th is 4x cubed, not just x cubed. But that's not a big deal. If I put a 1/4 out in front of that, then when I take the derivative, bring the 4 out, 4 times 1/4, those disappear, right? 4 times 1/4 becomes 1, and then I get an x cubed. So I need that 1/4 there in order to get just a plain old x cubed. And then, of course, I have a plus c. So there's the antiderivative, right? Now, I'm going to make it easier because we have a formula. Remember our basic formula, the very first formula we learned when we were taking derivatives was the power formula, right? So the derivative of x to the n was n times x to the n minus 1. Well, we have a power formula for antiderivatives. Here it is. The antiderivative of x to the n, okay, of any power term is simply this. X to the n plus 1, right? We've got to bump up the power over n plus 1. that over n plus 1 is what's happening up here. You need that to cancel things out, plus c. And that is the power rule. We will use that just as much as we use this power rule in differentiating. Because the rest of the semester is about finding antiderivatives, right? We've done all our work finding derivatives. Now we're going to find antiderivatives. Okay. All right. Now, we have a rule that says, we'll just write down a problem here. So now, if I want to find the antiderivative of 3x to the 7th minus 2x to the 6th plus 5x to the 4th plus x cubed plus x squared minus sine of x, right? Just go crazy here, right? There's our function. So the nice thing is, if we have a rule just like we do with differentiation. If I want to find the antiderivative of this big ugly mess, okay, I can just do it one term at a time. Okay. So I can just deal with the 3x to the 7th and then the 2x to the 6th. So those are power terms, right? So the antiderivative is of 3x to the 7th. Now the 3 is going to be a part of it. That's just like the coefficients that we had in differentiation. They just sit there, right? So the 3 is going to be there. And then we deal with the power term, x to the 7th. So the derivative is going to be x to the 8th over 8. Now just so you know, this will become 3/8 x to the 8th. Okay, so that's how that all works out. The 3 just sits there, and then we take the antiderivative of x to the 7th, which is x to the 8th over 8. And then, of course, then we multiply the 3 to the 8 over 8, right? So let's keep going. Minus 2x to the 7 over 7. Right? I love taking antiderivatives this way because it's just x to the power over that power. X to the 7 over 7, which cleans up to become 2 sevenths x to the 7 plus 5, x to 5 over 5, right? I'm just bumping up the power. Now those 5s cancel out, so I'm just left with x to the 5 plus x to the 4th over 4. So that's a 1/4 x to the 4th plus x to the 3 over 3. So that's a 1/3 x to the 3. You know what? This is, dang, I wonder. I don't think I started recording this. So this is not recorded for those that are not there. Darn it. All right. Okay, so continuing x to 3 over 3, and then the antiderivative of negative sine is going to be plus cosine. That's just plus cosine of x. And then that's it. We just tack our plus c. And that's the antiderivative. So you see, that's an incredibly complicated function. But to find the antiderivative, we just do piece by piece. All right? And so that's what you're going to see in this section. All right? I'll put up some other examples because clearly I didn't record this, so I'll put up some more examples for you to see. But there's kind of a brief overview of those two sections. Do you guys have any questions on those things? All right, I've already got examples up of L'Hopital's rule, so those will be good. But I'll put some more up for antiderivatives, and I might put up a few more L'Hopital's examples as well. So, all right, guys, give me a plus if you're okay, or speak up, or something like that. Okay. All right, guys, that should get you started on these two sections. Remember to follow those deadlines. I think I've got homework posted I don't have homework posted for 410 yet, but I'll get that posted. And then we'll just go from there. We'll just keep going. Remember, we're doing 2 sections each time, so next time we meet, we'll be moving on to other stuff as per the schedule. So anyway, we'll keep it covered. Let me know if you have questions. Send them to me in Canvas chat, and we'll go from there. Otherwise, have a great day.